Hello everyone. In this poster, I'm going to present our work on a new approach to probe non-standard interactions in atmospheric neutron experiments. We use the ICAL detector at INO as an example. So iron calorimeter detector, ICAL, at the proposed India-based neutron observatory, INO can play an important role in constraining NSI over a wide range of energies and a wide range of baselines. So ICAL is a 50 kiloton magnetized iron detector where RPC act as active detector element and iron act as passive detector elements. So the uniqueness about ICAL is that it can distinguish neutrinos and antineutrinos using the magnetic field of 1.5 Tesla, which can distinguish the charge of muon. ICAL is sensitive to the muon energy range of 1 to 25 GeV with a muon energy range of 10%. The baseline to which ICAL is sensitive is range from about 15 kilometer to 12,000 kilometer with an excellent angular resolution of about 1 degree. In this work, we are going to probe neutral current NSIs which occur during the propagation of neutrino through matter. So here this parameter epsilon mu tau, this represents the strength of this NSI, which is parameterized in terms of standard matter potential, which is equal to root 2 GFNE. So this metric shows the final modified Hamiltonian with in presence of NSI. So in this work, since we are dealing with only atmospheric neutrinos where mu tau channel is dominant, we choose to constrain epsilon mu tau only, and we in this work we are constraining only the real values, but both positive as well as negative values. So we use nuance neutrino event generator to simulate neutrino interactions for ICAL geometry using the neutrino flux at INO site. We use the 3 flavor matter oscillations with the frame profile using reweighting algorithm. Then we apply detector response function using the migration matrices provided by the ICAL collaboration. In this work, we are using the ratio of upward going and downward going reconstructed muon events. So in this plot, we show U by D ratio as a function of log L by E of reconstructed muons. On the left, we show plot for mu minus. On the right, we show for mu plus. Here we show 3 colors. Black one represents the standard case. The red is with plus 0.1 of epsilon mu tau, and the blue curve represents epsilon mu tau of minus 0.1. So here we can see that blue as well as red, they are getting shifted with respect to the black curve, and they are shifting in the opposite direction. If we look at the mu plus, then we see that this shift is in the opposite direction. For example, the red one is shifting to the left for mu minus and it is shifting to the right for mu plus. So we can say that this dip location D minus and D plus, they shift in the opposite direction. Now, let us see how this oscillation dip appears in terms of energy and cos theta of reconstructed muons. So here we show U by D ratio as a function of energy and cos theta of reconstructed muons, where this dark blue region shows the oscillation valley. We can see that this oscillation valley bends in presence of epsilon mu tau. So in the top row, we show epsilon mu tau of 0.1 plus 0.1. In the bottom, we show for epsilon mu tau of minus 0.1. The left is for mu minus and the right is for mu plus. So we can see that for positive epsilon mu tau of 0.1, the valley is bending in the upward direction. For negative epsilon mu tau, it is bending in the downward direction. And if we look at mu plus, then this bending is in the opposite direction. Now we fit this oscillation valley with this function fx comma y, where we have this parameter m alpha and alpha, where this m alpha represents the alignment of this valley and it is related to delta m square 32, and this parameter alpha represents the curvature of this oscillation valley, which is related to epsilon mu tau. So after fitting this oscillation valley, we obtain these white contours, which are shown by this white solid and dashed curves. We can see that this fitting function is nicely tracking the curvature of oscillation valley. Now we go to the results. So here in the left plot, we show epsilon mu tau as a function of delta D, and these blue dots represent the calibration curve where we vary the epsilon mu tau and calculate delta D. And this is done for a 1000-year Monte Carlo. Now using multiple sets of 10-year data, we obtain these gray bands which show the 90% bounds on epsilon mu tau. Here these dark bands show the results for fixed parameter and no systematic case, and the light gray band show the results for varied oscillation parameters and including systematics. In the right plot, we show as a function of delta m alpha and delta alpha, where delta m alpha is the difference of m alpha for mu minus and mu plus, and delta alpha is the difference of alpha for mu minus and mu plus. So here this blue line shows the calibration using 1000-year Monte Carlo for epsilon mu tau, and this black point shows the points obtained using 10 years of multiple sets. The gray region shows the region where 90% of the points are present. So 90% of the black points are present inside this gray region. The overlap between this blue line and this gray region gives us the 90% bounds on epsilon mu tau. So in this table, we show the results for from oscillation dip approach and oscillation valley approach for both the cases fixed parameter and varied parameter. So we can see that we obtain about 2% bounds on epsilon mu tau. The existing bounds from ice cube and deep core are also about 2% in our convention, and the results from super K are about 3%. So we can see that our results are also same as what is obtained using ice cube and super K. So now we conclude, using good reconstruction efficiency at ICAL for mu minus and mu plus, we can reconstruct oscillation dip and valley. Now here in this work, we have proposed a new approach to probe epsilon mu tau using oscillation dip and valley. So a new variable representing the difference in the location of dip for mu minus and mu plus is used to constrain epsilon mu tau. In an independent approach, we use the contrast in the curvatures of oscillation valley for mu minus and mu plus to constrain NSI parameter epsilon mu tau. Thank you for your attention. And if you have any queries, you can send me an email on this email, anil.k@iupb.res. Thank you.